In this video, we're going to talk about quadrilaterals. Quadrilateral, it's a geometric figure with four sides. That's it, right? We call it the quadrilateral PNQM, for example, right? Using the same notation that we use with triangles. It's very common that we use also like a little figure like this, right? To saying that it's a quadrilateral, maybe, right? In this video, we're going to talk specifically about parallelograms theorems. A parallelogram, it's a quadrilateral, so it has four sides, right? But it has both pairs of opposite sides parallel. So these two opposite sides are parallel, and these two opposite sides are parallel. All right, so let's start with the first theorem. The first theorem says or states that, all right, let's put it here, theorem. All right, so the first theorem tells us that if a diagonal is drawn, so if a diagonal is drawn, all right, in a parallelogram, then two congruent triangles are formed. Okay, so what this is saying is something like this. We have a parallelogram, right? So we have basically something like this, like we had in the previous page or image, right? Let me do this a little bit better. And we have this, right? Okay, so maybe this is parallelogram A, B, I don't know, C, and D, right? And it says, if a diagonal is drawn in a parallelogram, so this is a parallelogram, right? And I draw a diagonal like this, then two congruent triangles are formed. So now we have the triangle ACT. So triangle ACT, it's congruent with triangle ABD. Okay, so before doing the proof of this theorem, let's make a plan, all right? So we need to prove that the two triangles are congruent. To prove that triangles are congruent, we have some criteria that we might use to prove it, to guarantee that. And those options that we have are this. We have side, we have side, angle, and we basically have angle, side, angle. That is pretty similar to angle, side, right? And you notice that in this two triangle, this AD, it's a common side, right? So we know that we have a side, so we only need to look for two angles to be able to prove it, right? Because if we choose this, then we're missing one side and one angle, and if we're choosing this, then we're missing two sides. So it will be somehow better if we try to have this, right? But we also notice, if you remember, that since this is a parallelogram, two of this pair of sides are parallel, right? We also know that AD works as a transversal. So if it's a transversal, then we also know that these angles, the alternate interior angles, are congruent. And if this happens, then it will happen on this side. It will happen on both sides. And let me use a different color so you can see it better. So it will also happen on this too. Then you know that the two triangles are congruent, right? So that's basically our plan, going for ASA, noticing that we have some properties going on in the two triangles. All right, so let's put names to this angle. So this is angle 1, this is angle 2, and let's call this angle 3, and let's call this angle 4. Okay, maybe it's a little bit cramped, but I think you should be able to see it properly. So remember that we have statements. So we have statements, right? And we have reasons, right? Okay, our first statement, it's that AD, it's a diagonal. It's a diagonal, right? Diagonal. And also, we know that we have a parallelogram. So ABCD is a parallelogram, right? This is our given. Okay, number 2. we immediately notice that AD, it's congruent with AD by common side or reflexive property. So reflexive property or common side. Common side. It's a common side in between the two triangles. Okay. Remember that AD is a diagonal, so it also works as a transversal because since this is a parallelogram, AB, it's parallel with CD. So AB, it's parallel with CD because, or our reason, it's because ABCD is a parallelogram, right? Okay, so if this happens, then we know that angle 1 and angle 2, angle 1, it's congruent with angle 2, with angle 2, and angle 3, it's congruent with angle 4. So angle 3, it's congruent with angle 4. Okay, and all right, I'm taking a little bit too much space here. I'm going to erase it. And I'm going to draw a parallelogram so we know what we were talking about. So this is true because alternate interior angles, right? Angles. Okay, so now we have angle side. So we know that the true triangles, triangle ACD, it's congruent with triangle ABD. And this is by angle side angle. Remember, 3 and 4 are congruent, are corresponding, are alternate interior, my bad. Angle 1 and 2 are alternate interior. So the triangles are congruent because we have angle, side, and an angle, side, and an angle. Okay, so that's how you prove this theorem. Okay, from this video, we have a couple of corollaries that we can establish, all right, or define. So corollary 1, we're going to have a couple. It's opposite angles of a parallelogram are equal. So what this is saying is that we have a parallelogram, maybe a parallelogram like this, right? Okay, this is way too long. Like this, right? The opposite angles are congruent. So these two are equal or congruent, and these two are also congruent, right? So if we name this parallelogram A, B, C, D, what we have is that A is congruent, angle A is congruent with angle D, and angle C, it's congruent with angle B. All right, so this is what this corollary is saying. Corollary 2. So corollary 2. All right, corollary 2 states that opposite sides of our parallelogram, so opposite sides of a parallelogram are equal or congruent, right? So again, what this is saying, and I'm going to use a similar figure. If we have this parallelogram, right? This parallelogram, what this is saying is, if this is A, B, C, D, what this is saying is that this side is congruent with this side, and this side is congruent with this side. All right, so basically we can define that CD, it's congruent with AB, and that AC, it's congruent with BD. All right, that's what we can have from these two corollaries. So let's go for a third one. So corollary 3. Corollary 3 states that two parallel lines are equidistant throughout. All right, throughout. What this means is this. We have two parallel lines. So let's suppose that we have this line, and we suppose that we have this line, and we can prove this In a second, we can prove this. What this is saying is basically, imagine that we can draw two perpendicular or several perpendicular lines, right? We know that perpendicular lines, two perpendicular lines, all right? And we know that if we have perpendicular lines, these two are 90-degree angles. So what this is saying, and let's put names to this, let's call this A, let's call this B, all right? Let's call this C, let's call this D. What this is saying is, no matter how many of these lines I draw, what's going to happen is that every line is going to be equal to the other. So this is going to be congruent with this, because if it's saying that it's equidistant, it means that it has the same distance throughout and between these two. No matter which position I choose, this distance will be always the same thing. Okay, this is what the corollary, or this theorem, it's saying. We can prove this. We didn't prove the other two. I guess that you can do it on your own, but we can prove this because it's really interesting. Let me move this figure here. Okay, all right, let's move it there. And remember that we have statements. We have statements, and we have reasons. All right, let's put it here, reasons. Okay, so our first statement, it's basically, we know that AB is parallel to CD. So AB, it's parallel to CD. And this is given, right? This is given. And basically, we have another given, because since it's saying that is are equidistant throughout, what we need to show or prove is that no matter how many perpendicular lines we draw, all those lines are congruent. So another given is basically that AC, it's perpendicular to CD, right? So that's why we have this 90-degree angles. And also that BD, it's perpendicular. Actually, let's put it here. BD, it's perpendicular to CD2. CD, all right? So all this is given, okay? Number two. Okay, from the corollary number 2, we already established that opposite sides of a parallelogram are equal. So basically, if we show that this is a parallelogram, we can show that these two are equal, okay? And for this, we know, since these two are 90-degree angles, we know if two lines are perpendicular to the same line, then they are parallel to each other. That is a theorem that we know from a while now. So we know that AC, it's parallel to BD, right? Why is this? Because if two lines are perpendicular to the same line, basically, then they're parallel to each other. Then they are parallel to each other, right? And okay, so we know this, and if we know that AC, it's basically parallel with BD, and AB is parallel with CD because, well, of the given, because we know that there are parallel lines, then we can form a parallelogram. So basically, we can form a parallelogram. So parallelogram, or the figure AB DC, it's a parallelogram. Why is this? Because of the definition of parallelogram. Right? So if this is a parallelogram, by corollary number 2 that we just discussed, we know that the opposite sides are congruent. So AC must be congruent with BD. And this is by opposite sides. So opposite sides of a parallelogram are congruent, right? Or, well, let's use the word congruent, right? So that is the general idea for this corollary. We have a 4 corollary. Corollary number 4, corollary 4, states that consecutive angles of a parallelogram are supplementary. So if you remember, you have, or two angles are supplementary if when you add their measurements, the result, or they are equal to 180 degrees. Okay, so let's try and do an example in which we apply some things like this. So let's do an example, okay? Let's suppose that we have this parallelogram. So we have this parallelogram, okay? And the parallelogram is called RSTV, okay? And we know that the measurement of angle S, it's equal to 42 degrees. We know that ST, it's equal to 5.3 centimeters. And we know that VT, it's equal to 8.1 centimeters, all right? 0.1 centimeters. And remember, this is a parallelogram. So RSTV, it's a parallelogram. This is really important. So if I ask you to find, for example, the measurement, find the measurement of angle V, what would you say? Well, if you notice, you probably do, S is right in front of V. And we already know by the corollary, one of the corollary, if you remember, it's corollary number 1. The two opposite angles are congruent. So angle B should be the same as angle S. So it will be 42 degrees. What if I ask you to find the measurement of angle T, right? We already know that consecutive angles of a parallelogram are supplementary. And these two are consecutive angles. So we know that angle V, or the measurement of angle V, plus the measurement of angle T will be equal to 180 degrees because they are supplementary. If this is true, we know that the measurement of angle V is 42 degrees. So 42 degrees plus the measurement of angle T will be equal to 180 degrees, right? And well, if we subtract, this is a small equation. If we subtract on both sides, right, this is gone. And now we know that the measurement of angle T will be equal to 180 minus 42, it will be 182 degrees. And this will be the measurement of angle T, right? So this is basically an application of all those corollaries to find information on a parallelogram. I can even ask you other things like what would be the measurement of RS, or what would be the measurement of RB? If I'm looking for RB, you know that it's right in front of ST. So it's opposite, right? ST, this one right here. Let me find it. This one, right? ST. And ST is congruent with RB. So we already know what RB, the measurement of RB is, right? And also we know that for this one, for BT, that is 8.1. This is VT. This one right here is VT. Then we have the measurement of RS. So this is RS. Well, this doesn't look too bright. So RS, right? So we're looking basically for this, right? So there you go. That's how you use corollaries to find information in a parallelogram. Okay, let's do a final example. So, well, this is more like another proof, but it's basically the same. So we have the given, and the given is that A, B, C, D, it's a parallelogram. So we have parallelogram A, B, C, D, right? And I'm asking you to prove that AC and BD bisects each other, right? Bisects each other, okay? I'm asking you to do this. I'm going to give you the figure. So maybe we have this parallelogram. So we have this parallelogram. Okay. The parallelogram is A, B, C, D. Let me draw the points. Sorry if it doesn't look perfect. but this is the idea. So what I'm asking you is that this line right here and this other line bisect each other. So this point make this and this congruent and this congruent. That is basically the problem. Okay. All right. So we know where we're going, and we know also that these two are parallel and these two are parallel. All right. Okay. So the given states that AC and BD are diagonals basically, and we have that this parallelogram. Okay. Or we can add them by construction. It doesn't matter. But the thing is, it's that AC and BD bisect each other. We need to show that these two things, these two line segments are congruent, these two line segments are congruent. All right, and to show that, we basically need to prove that the two triangles are, that all the triangles that we have here are congruent. Like if we prove that this triangle is congruent with this triangle, then we know that these two sides, corresponding sides, will be congruent. Right? If we prove that this triangle is congruent with this triangle, we will prove the same thing. So we need to find information that allow us to do that. For this, let's call this M. All right, the point in the middle, let's call it M. We know by definition of parallelogram. Let me erase these marks. We know that this side must be congruent with this side, right? So we have side and a side, right? What else can we find? Remember that this is a transversal. This is a transversal. If this is a transversal and these two are parallel, then the alternate interior are congruent. So these two are congruent, right? And if this is also a transversal, for these two parallel lines, this is also alternate interior, and they're congruent. So now we have angle, side, and an angle. Angle, side, and an angle, and the two triangles are congruent. And then we can prove that the two things are congruent, right? So let's use all that. So we have statements, and we have reasons, right? First, our first statement is that we have parallelogram A, B, C, D, and AC and BD are diagonals. All right, this is given. Let me put it a little bit more to the right. So reasons, and this is given. All right, number two. We know by one of the corollaries that we just studied that opposite sides in a parallelogram are congruent. So AB is congruent with DC. We already established that. And this is by opposite sides of a parallelogram are congruent, right? And number three. We already know that these diagonals are transversals. So, and let me put names to this. Let's call this angle 1, this angle 2. Let's call this, and let me write a different color, this angle 3, and this is angle 4. So we know by alternate interior angles that angle 1 is congruent with angle 2, and angle 3 is congruent with angle 4. So angle 3 is congruent with angle 4. This is because alternate interior angles. So alternate interior angles, right? This is number 3. Number 4. So we already have basically everything. Triangle, AMB, it's congruent with triangle DMC. This is why by angle, side, angle, right? We have angle, side, and an angle. Also, if you remember, by corresponding parts of congruent triangles are equal, we can say that these sides, these corresponding sides, are congruent. So now we know that BM or MB, doesn't matter. BM, it's congruent with DM, and that is something that we need to prove, or the idea that we needed to prove, because it bisect each other. So there must be equal. So BM, it's congruent to DM, and AM, it's congruent with CM. And this is why by corresponding parts of congruent triangles are equal, or CPCTE. Okay. By definition of bisector, if we know that they are congruent, then AC and BD bisect each other, right? And this is basically why, because definition of bisector. Okay, so this is the idea on how to use these theorems to solve problems related to quadrilaterals or parallelograms. In the next part of this series of quadrilaterals, we're going to keep talking about some theorems related to parallelograms. So see you in the next video.